So I want to start by introducing myself. So I'm Aisha B. Rahman. I'm the chair of IEEE Women in Engineering Albuquerque Section Affinity Group. And I welcome you all to the monthly public talk series of our Affinity Group. Today, as our guest speaker, we have Dr. Shuya Wei, and she's joining us. And she is an assistant professor in the Department of Chemical and Biological Engineering here at UNM. She obtained her PhD in chemical engineering from Cornell University in 2017 and her BE engineering in bioengineering from Nanyang Technology University in 2013. She was a postdoctoral fellow at Massachusetts Institute of Technology from 2017 to 2019, and her research focuses on understanding the fundamental aspects of electrochemical processes occurring in electrodes and at electrode or electrolyte interfaces. Building on this knowledge, she aims to develop advanced metal-based batteries with high energy density for applications in energy and the environment. Today, she will be giving a talk on rational design of interfaces to enable high-energy metal-based batteries. So thank you so much, Dr. Wei, for taking time out of your very busy schedule to join us. We really appreciate it. Also today joining us are our Affinity Group members, our Vice Chair, Ariana Santa Maria Peñafiel, and our Affinity Group Advisor, Dr. Siropulo. And before starting the session, I would like to ask Dr. Siropulo to say a few words on the behalf of our Affinity Group.
Thank you, Aisha. First of all, my apologies. My camera doesn't collaborate with me today. Our group is a relatively small group, but quite active. And we are very lucky that we have also so passionate presenters that they accept our invitations to present in our monthly meetings. I don't want to take more time from Shuya, so I think that I will pass the floor to Shuya, and thank you so much for accepting our invitation for today.
Okay, thank you, Aisha and Rini, for the nice introduction and invitation. I'm really excited to share our group's research in this Women in Engineering section for your monthly public talk. I'm gonna go ahead. So we all know that batteries are very important. That's very obvious, right? So let's see. To achieve net zero emission and to protect our climate, we all want to move forward to renewable sources of energy like wind or solar. But what will happen when the sun doesn't shine or when the wind doesn't blow? We need energy storage device to store the harvested energy. And meanwhile, at the same time, we need laptops and our cell phones, which are long-lasting, safer, and low cost. And it seems like we all run into trouble of that. So we have to move forward to a different battery chemistry. And this chart here shows different battery chemistry and their maximum energy density. And there are a lot of points in this chart, but I just want you to focusing on the black star, lithium-ion batteries, and the red star, category of metal-based batteries. The black star is the commonly used lithium-ion batteries which are in our cell phone, but the red star is the future metal-based batteries. All these batteries use ions as a charge carrier, but what makes metal-based batteries so powerful compared to lithium-ion batteries? To answer this question, we have to look what's inside these batteries. In the lithium-ion batteries, there is a graphite-based anode which intercalate with lithium-ion, and on the cathode side, there is a lithium-based compound. However, in the metal-based batteries, we just throw away graphite on the anode side. Instead, we just have a piece of metal. By doing so, we can save a lot of weight on the anode side, so the energy density of the anode can be increased by 10 times. And since we already have ion source on the anode side, we don't need to use some metal-based compound as a cathode. So one can just use some simple molecules like sulfur, oxygen, and so forth. They can react with lithium or sodium ions to form sulfide carbonate by conversion reaction. In that way, the overall energy density is very high because of the large number of electrons involved in the electrochemical reaction. So I've shown you in the metal-based batteries, there is a lithium or sodium metal anode, and there is a small molecule cathode on the other side. In the middle, we have an organic liquid electrolyte, which transport ions from one side to another. And there is also a plastic paper sheet that we call it a separator that prevent any electronic connection between the two electrodes. During battery operation, metal ions move and deposit on the metal anode side during the charge cycle. And during discharge, those ions move and react with the cathode. You would expect this process to happen over and over again for hundreds of cycles. However, during the charge process, you will find that these ions deposit at the rough structures on the anode side, and they call dendrite. This video here shows the sodium electrode surface after several minutes of charging. Here, this bottom part is a piece of sodium metal, and the upper clear field is the electrolyte. We directly visualize sodium dendrite growth through an optical microscope, and you can see there are a lot of black mossy dendrite formed, and this dendrite can easily pierce through the separator and ultimately touch the cathode to cause a short circuit. Typically, the common electrolyte used in the batteries are flammable, and any shot can generate ohmic heat, and this heat can cause fire explosion. And this is also the reason why people consider lithium-ion batteries is not safe in the market, because once you overcharge the batteries, this dendrite is also going to form on the graphite anode side. And this is in fact seen in other sorts of metal as well, like lithium, copper, zinc, and so forth. But this phenomenon is less likely seen in magnesium metal. And why this dendrite is so commonly formed on the metal electrolyte interface? So that's what brought us. We thought dendrite growth is not intrinsic property of the metal, and there must be some transport process fundamentally going on at the metal electrode interface. So now let's take a closer look at the lithium electrolyte interface. Here, I hope you don't need to worry too much about whether the metal anode is lithium or sodium, or even later I'm gonna talk about aluminum or zinc. As I mentioned earlier, this dendrite formation is very common in almost all kinds of metals. So here I'm seeing that lithium metal can react in the presence of an electrolyte to form a passivation layer. We call it a solid electrolyte interface. This solid electrolyte interface is very inhomogeneous in nature. So some parts are more conducting and some parts are less. And then lithium ions selectively deposit on the metal with higher conductivity and form those sharp nuclei. And once these nuclei are formed, there is a cascade event coming from here because the local electric field on the tip of this nuclei is very high. So the ions continue to deposit on the top of this nuclei, and then this nuclei turn into dendrites that can short the cell. So overall, what I'm saying here there are two sorts of instability during battery charging. The chemical instability due to the reaction on the surface, and also the morphological instability due to the growth of dendrite. So if you look at the orange of those dendrite formation for reactive metals, this is because of the formation of nuclei on the metal surface, and the nuclei are formed because of the passivation of the metal surface. Previous research has shown that previous research has shown that lithium is thermodynamically unstable in the presence of any kind of solvent. So you have an electrolyte that will react with metal to form different species at the interface. And people have found that on the interface, there are different types of salts and decomposed electrolytes like lithium carbonate, lithium oxide, and so on. So the question here I want to ask is that, how does each of these composition affect ion transport in SEI? To answer this question, we collaborate with Ariel's group at Cornell and performed the DFT calculations of binding energies for most stable surface for species that can commonly seen in the solid electrolyte interface. Here, this gray bar is calculated in vacuum condition, and the red bar is performed in the existence of solvent, but I hope you don't dig into that. And then we define a new term here, the diffusion energy barrier, which is the energy required for the ions to hop from one stable region to another. And what we found interesting here is that the diffusion barrier of magnesium metal is much lower than lithium or sodium. That probably helps us explain why magnesium is less likely to form dendrite. What happens here is that if the surface diffusion barrier is lower, the ions can easily migrate on the surface and nucleate in a flatter manner. And we notice that the surface diffusion barrier is much higher for lithium carbonate, which is a typical SEI forming salt. And that's probably why dendrite are always formed. However, we also found that halide salt has very low diffusion energy barrier, and sodium bromide is as low as magnesium. So this brought to us that if we have halide salt on the solid electrolyte interface, we can have a very low diffusion energy barrier and probably a higher stability. To test this theory, we react with the pristine sodium metal with bromopropane to form a fine layer of sodium bromide on the electrode surface. And then we did a couple of electrochemical battery testing that I'm not going into detail, but you can definitely see that, sodium bromide coated battery electrode can run more cycles and are more stable compared to the pristine sodium metal anode. And to testify whether this halide salt interface can be applied to other type of metal anode, we also studied the additive of aluminum iodide to stabilize aluminum metal battery. And there are some more electrochemical testing results showing that when we have this aluminum iodide as the electrolyte additives, we can demonstrate a much stable aluminum symmetric battery cell by showing the smaller interfacial resistance and the small as well as smaller overpotential in a long-term stripping plating test. And if you look at what are the electrode deposition morphology for aluminum metal looks like in the presence of aluminum iodide and without aluminum iodide, it's also clear that with aluminum iodide, the aluminum deposition shows a much flatter manner compared to the case without aluminum iodide in the electrolyte. So this helps us explain that this halide salt can help us stabilize the solid electrolyte interface and achieve a much longer cycling performance for batteries. So now we have some idea to deal with dendrite formation on the reactive metals, and we can move forward to the next stage to stop dendrite growth. And this has to do with ion transport in the electrolyte. There is a framework that proposed by Shuya, where he questioned about why do dendrite grow in the first place. To answer that question, he built a simple model for the battery, where he basically had a cathode and anode and electrolyte with cations and anions. And then he wrote down conservation equations for every species in the electrolyte. For example, these are the conservation equation of mass for cations and conservation of mass for anions. And this is a constitutive equation for the flux of cations. So it has a diffusion, the first term, and also the electromigration, the second term. And he did the same thing for the anions. And of course, all this happen in a battery that operate under electric field. So you also write down Poisson's equation that describes the conservation of the field. So these are some simply enough differential equations. And we can then solve those differential equations and get a profile shown on this top. So this is a profile for the concentration of cations and concentration of anions, which is a function of distance in the cell. And what we found interesting here is that we found the solution in the electrolyte can be divided into two regions. The first region is called region 1, where electron neutrality is actually huge, meaning that the concentration of cation ions and concentration of anions at everywhere are the same. You can see that because you cannot see any difference between the lines of cation ions and anions in region 1. And that's normally what you expected in the system with charges. But there is a second region called region 2, that's near the anode, also near the zone of instability, where you can find that the concentration of cation ion is slightly higher than the concentration of anion. And this region is called the region of space charge. In another word, the electrolyte has a net positive charge in this region. If you think about what it means under electric field, there is a body force now in the electrolyte that drive electrolyte motion in the cell. And Flurry shows that under such a body force in a closed cell, you will have electrodeposition looks like those green lines. In another word, the electrodeposition profile is like you dig materials in the valley and then dump them on the peak. So this is how dendrite grow. And we also use experiment to show that this phenomenon is very obvious from the prediction, where you can see that electrodeposition on tip of those dendrite grow much faster compared to the bottom side. And that's why dendrite always grow. So you may see that from those models, there are a couple of parameters that determine how this dendrite grow and what to change the concentrations of cation and anion in the electrolyte. And we are interested in how those physical parameters is going to affect battery performance. To answer this question, our group have built a model that account for several different factors of battery performance. So we basically wrote down the conservation equation that's basically the same as before, except for the conservation equation of flux. It has a diffusion electromigration, but it also has a pressure term. The pressure term comes from the fact that the separator of the cell is solid. When dendrite grow and form a bump, that bump form a compressible wave in the electrolyte that can generate stress, and stress can generate displacement, and displacement can generate pressure. And the pressure can generally change the kinetics of the reaction in the interface. So it's still a set of many equations we can solve. We solve those equations using a technique called linear stability analysis, where the idea is that you perturb the interface and see whether the interface grow or shrink. You can characterize this perturbation by using sigma, the perturbation coefficient. When sigma is positive, that means you have dendrite formation. When sigma is negative, that means you have stable electrodeposition. And then there are several transport parameters in those equations that we can tune to design a better battery. One example is that if we want to eliminate the space charge in the near the electrode, we can put some fixed anions near the electrode to neutralize the space charge. But how many fixed anions do we need? So we plot sigma, the growth rate, versus cat, the inverse nucleus size, the wave number. And this plot tells us the stability of the growth rate by changing the amount of fixed anions in the electrolyte. And when you don't have fixed anions, the deposition is unstable. So just like the prediction by Shaswell, when you fix all anions in the electrolyte, the sigma is always negative. So that means you always have stable electrodeposition. So this is like a single ion conductor where you only have cation ions moving in your electrolyte, and you will always have stable electrodeposition. However, this is not always happening in real case, but somehow we can mimic single ion conduction by limiting the ion transport of anions by creating a different type of electrolyte. We call it ionic liquid. So in the following example, I'm showing you the electrolyte, the new electrolyte we have developed in our group, which is just composed of cation ions and anions in this example. So here the idea is if we don't use solvent in the electrolyte, we can somehow regulate ion mobilities in those ionic liquid electrolyte. So our group have developed a ternary-based ionic liquid electrolyte that composed of two types of imidazolium chloride salt as well as aluminum chloride salt. And in this kind of electrolyte, there are no solvent being added to the electrolyte. And we have been figuring out what we can do, what's the optimal ratio allow us to achieve a liquid phase for those salt which exist as solid by themselves. And our hypothesis is that the alkene chain containing imidazolium cations will dominate some van der Waals interaction to form some liquid mixture when we mix them together. And further addition of the aluminum chloride will cause a Lewis acid-base interactions with the imidazolium chloride that can form a liquid phase at room temperature. And then we run some electrochemical tests to see whether those electrolytes allow us to achieve a stable electrodeposition. And you can see from the cyclic voltagram that the ternary phase eutectic electrolyte is much active compared to the binary phase. And again, from the stripping plating test where you charge and discharge this battery for many cycles, you can also see that you're able to achieve a quite stable voltage profile for like hundreds of hours. And then we were trying to see if we are able to demonstrate some stable metal-based batteries. So we pair this electrolyte with aluminum as anode and also some carbon as a cathode to see if they are able to sustain a good performance. And what we found interesting here is that when we use graphite as a cathode in these aluminum ion batteries, although it can sustain for a few cycles, but it cannot run for very long. And when we open the cell to see what's happening on the cathode side, we see exfoliation and breakdown of those graphite flakes. That's probably the reason that caused the battery to be fail. And then we switch to another type of carbon graphene as a cathode and run for charge-discharge test. And then it turned out that graphene can be cycled stably for hundreds of cycles and even at a much higher current density. So here, if you look at the current density applied for those aluminum ion batteries, there's 2 ampere-hour per gram and 4 ampere-hour per ampere per gram represents a really fast current charge rate for these batteries. It basically means you can fully charge your cell in less than 5 minutes. Imagine right now, you always want to charge your cell phone for over hours in order to get a fully charged cell. And we believe those electrolytes is a key that allows this battery to be able to charge in a very fast rate. So next, I want to show you some other strategies that allow us to control the morphology of dendrite by engineering the metal anode in this example. So here we actually proposed a porous metal electrode to help stabilize the electrodeposition. And our hypothesis is that if you have a porous metal anode, once you apply a current, the effective current density can be reduced because of the high surface area of those porous metals. And in such way, you can reduce the effective diffusion limiting current in the porous electrode to achieve a stable electrodeposition. And to prove this idea, a student have fabricate different porous zinc electrodes with different particle size from 60 nanometer to 150 micrometers. And then we also did a couple of different electrochemical testing to validate the battery performance. And here I just want to show you how the morphology of those electrode deposition looks like when we use scanning electron microscopy to look at the zinc metal electrode surface after several cycles of charge and discharge. You can clearly see that when you have a planar zinc electrode, there are some hexagonal zinc plate being formed that grow perpendicular towards the electrode surface. And when we further use some porous zinc electrode with some higher particle size, you tend to see that those electrode deposition tend to be more flatter and spread on the electrode surface. And this is a direct evidence showing that those porous zinc can reduce the effective current, diffusion limiting current density to achieve a stable electrode deposition for metal electrode anode. Okay, now I hope I gave you some idea about our approach to address the instability in the anode electrode interface. And when you want to use metal as the anode and build a full metal batteries, you also want to pair it with a working cathode so that you have a real battery that can store enough energy density. And now I'm going to share you some idea about our approach on the cathode design to enable a full rechargeable metal-based batteries. And I'm going to focus in our strategies on designing metal CO2 batteries in this talk. At the beginning of this project, due to the pandemic, we have to, due to the pandemic and the lab shutdown, my students have to just stay at home and do literature search at the beginning of this project. So we were just looking at what are the all aspects for metal CO2 batteries and what are the candidate anode materials and cathode material and what kind of strategies can be implemented in order to develop working metal CO2 batteries. And this inspired us to dig into the aluminum CO2 battery as our interest. So what we found interesting is from the understanding of the literature, we found that people have demonstrated some mixed gas aluminum CO2 batteries by introducing both carbon dioxide and oxygen to enable a full discharge, to enable a long discharge plateau in this example. And the authors propose that oxygen being introduced in those aluminum CO2 batteries serve to speed up CO2 degradation, where oxygen is firstly being reduced to some superoxide, and this superoxide then react with the carbon dioxide when battery discharge, and then recycle back to oxygen. And the role of oxygen in this battery is serve as a redox mediator. And this allows battery to discharge, but oxygen is going to be detrimental to batteries because those superoxide are very reactive. And that's why those batteries can only be demonstrated as the primary batteries. And the reverse process is going to be very hard to achieve. Then this actually brought to us, we were thinking, are we able to replace oxygen with a redox mediator that can be more stable, that can enable both charge and discharge process? So again, we think about aluminum iodide as the redox mediator for the cathode side. And our lab has built some homemade switch lock cell for those metal CO2 battery, which allow us to introduce different gas atmosphere in those battery for the charge and discharge electrochemical test. And in this case, we have aluminum metal as an anode, and also we have a carbon black, a commercial carbon black as cathode. And we use ionic liquid electrolyte plus a small amount of aluminum iodide as additive and serve as a redox mediator. And then we performed a couple of an electrochemical test to see whether we are able to use aluminum iodide to enable battery discharge. And you can clearly see that when we introduced both aluminum iodide and CO2 in the batteries, we are able to achieve a quite stable discharge plateau around 1.1 volt that can allow us to achieve a really high capacity that close to 9,000 milliampere hour per gram. And if we just have aluminum iodide in this switch lock cell, we really get any capacity. And this is the same for the case where we just introduced CO2 in the gas and without aluminum iodide, and we really get any discharge capacity as well. So this makes us believe that we are able to use aluminum iodide to enable battery discharge in aluminum CO2 battery. And then we also want to demonstrate that these batteries can be reversibly charged for many, many cycles. Then we perform some other electrochemical tests to see the cyclic voltammetry and the galvanostatic cycling test and check if we are able to enable the recharge process. Again, you can see that and this aluminum iodide also allows this battery to recharge. And we see a very consistent discharge plateau in many different cycles. And there is also a linear relationship between the scan rate and the peak current in CV, which also suggests a reversible redox reaction. And together, all those results show that we are able to use aluminum iodide to demonstrate a rechargeable aluminum CO2 batteries compared to the previous primary aluminum CO2 battery. To further prove that whether we really have aluminum CO2 battery or it's just some other kind of side reactions, the previous study shown that the discharge product from their primary battery is aluminum oxalate. So here, what we demonstrate is that we actually build a fully discharged batteries. In this case, the anode is a piece of aluminum metal and cathode is some carbon mixed with aluminum oxalate. And there is no carbon dioxide being introduced in the batteries. And we show that the CV for these fully discharged batteries agree very well with our aluminum CO2 battery. And this also demonstrates somehow we successfully build a rechargeable aluminum CO2 battery by introducing aluminum iodide. And also we want to identify, do we really have aluminum oxalate as our discharge product, or do we really have any solid discharge product from carbon dioxide? So here what we did is we look at our cathode, the nickel foam cathode in the batteries after charge and discharge to see if there is any precipitate. And you can clearly see that when we discharge the batteries, we have some precipitate being formed on the cathode side. That's probably from the CO2 fixation. And during the charge process, most of those precipitate disappeared. This also suggests we have a reversible aluminum CO2 battery. And then the next step is to validate whether we what's the discharge product from CO2. Like when we have CO2 react with aluminum, what kind of reaction product do we form? And although the previous study suggests they have the aluminum oxalate as their discharge product in the primary battery, we also need to validate if we have the same product. And we use the aluminum NMR to show what's the discharge product in our example. Here you can clearly see the NMR spectrum from aluminum 27 NMR for our discharge cathode product agree very well with the aluminum oxalate. And although you can see a peak here, this peak represents the signal from the electrolyte. And you might see there is a slightly shift from the standard aluminum oxalate sample compared to our discharge product. And we hypothesize that this is due to the ion interaction between the discharge product and the electrolyte. So we further do some more NMR studies to show if we can correlate those peaks much better. And you can see that when we have this aluminum oxalate standard mixed with our electrolyte, this peak is going to shift backward a little bit. So that's basically proof that we also have this aluminum oxalate as our discharge product in aluminum CO2 batteries. And then how does this aluminum iodide enable a reversible CO2 utilization? And this is still an ongoing research we are working on. We hypothesize that using this aluminum iodide is a redox mediator that enable the reversible charge and discharge for our aluminum CO2 batteries, where when we firstly have this aluminum iodide ALI3 being introduced in the electrolyte, the solvate ion iodide species I minus can be oxidized to form some reactive species I3 minus, and this reactive species can further this redox process can convert CO2 to some oxalate product. So this is what's happening during the discharge. And then during the charge process, those reactive species I minus, I3 minus is going to react with the aluminum oxalate to decompose it and form I minus, and then aluminum oxalate is going to be decomposed to carbon dioxide, and then aluminum iodide will regenerate to its initial species. This is our current hypothesis about what's actually happening for the role of this redox mediator in enabling the reversible aluminum CO2 batteries. And we're still in the process of investigating what's the fundamental mechanism for this redox mediator in this aluminum CO2 battery. Okay, so now let me summarize what I have told you in the in my talk. I hope I convince you that those batteries based on some reactive metal anodes can be stabilized in some liquid electrolyte with the addition of halide salt. And there are some unstable mode of electrodeposition of metals that's going to depend on the number of unmobile anions in the electrolyte. And you can basically demonstrate some single ion conductor or ionic liquid to stabilize the electrodeposition. And you can also use porous electrode to stabilize electrodeposition by lowering the effective diffusion limiting current. And in the end, I hope I convince you that cathode and electrolyte design are very important to realize a rechargeable metal CO2 batteries. And overall, we want to understand the interfacial chemistry and ion transport in order to build a better battery. With that, I would like to acknowledge my group members and collaborators and funding agencies that support my group. Thank you. And this is how my group looks like. The most of the research I present here were done by Chris Fetchel, Gustavo, and Matt Paul, as well as my postdoc Raju. So now I'm going to share a little bit about my experience as a female faculty and working in the energy storage and science and technology field. I'm a first generation college graduate in my family, but my parents has always been inspiring me to pursue advanced degrees because they believe this knowledge can change people's life, and that they always encourage me to pursue college or even graduate degree. And that's also what inspired me to dig into knowledge. And I always believe fundamental knowledge is a key to solve complicated problems. And although there are many different problems in different fields and also different research areas, they are all related to the fundamental problems. And if you want to solve problems, I think fundamental knowledge is always a key. And I hope I can inspire more students from a very diverse group to go into the STEM field, and also to inspire more students to work on the clean energy technologies, because this was what our nation need for the future. Thank you for your attention, and I'm happy to answer any questions.
Thank you so much, Dr. Wei. Does anybody have any question? You feel free to unmute. No. Anyone?
I think that the Tamola tried to say something. I'm not sure that we can hear him very well. He can type it alternatively on the chat.
Yes. Okay, so he says, are there any sustainability or environmental concerns when developing the batteries that you have talked about?
Well, that's a great question. Yeah, this is something people need to think about. Although we claim that we are using, cleaner materials compared to lithium-ion batteries, but to be honest, there are always some pollutions in the series of material manufacturings in the clean energy technologies. For example, aluminum refinery is a really carbon-intense industry to produce aluminum. This is something people have to take into account. In addition, in all kinds of material synthesis for the electrolyte and purification process, there will always be some side product and chemicals being produced that's not going to be very easy to recycle. And I think this is a very good question, and the environmental and safety concerns exist in every aspect of material or chemical manufacturing industry that people have to take into account. But ultimately, I hope in the future, if we are able to build some reversible aluminum CO2 batteries that can sustain longer cycles, and it can be built up to the aluminum refinery industry, so that it can harvest carbon from those pollution, very carbon intense industry.
Thank you so much. Any other questions?
I have a question. So, hello, Dr. Wei. So my question was, what do you see as the most significant challenges or opportunities in the future of interface design for high energy metal-based batteries?
That's a great question as well. Interfacial design is a key to achieve a high energy metal-based batteries, because if you look at batteries, it's much simpler than, let's see, if you look at your cell phone, battery is the only component that store energy, but it's much simpler than the other electronic components inside the batteries. So the active materials in batteries are just three components. You have cathode, anode, and electrolyte. So basically just three active components in batteries. And in order to make a working batteries, you always want to rely on the interfacial reactions to achieve a stable charge and discharge, and to allow your battery to run much longer. Interfacial design, I think this is the key to achieve high energy batteries for the future. And also, I think this is a key for current lithium-ion batteries. You always want to make sure you have a very stable interface in order to achieve longer cycles, and also for the battery to run much safer. I think this is the key. You have to learn the fundamentals and think about how you can design a stable interface that allows both ion-based batteries and metal-based batteries to run longer cycles. And then for conversion reaction batteries, for example, the metal-based batteries, interfacial design is actually more challenging because you are basically having some chemical reaction happening at the interface that's going to change the phase and change the change your molecules at the interface. They also require more engineering design and fundamental understanding in order to make those metal-based batteries to work.
Thank you so much. I'm going to ask a question, and I may be the last. So it's going to be a generic question. So I want to ask you, for those interested in pursuing research or work in this field, so what would your advice be for them? Like, what emerging areas within battery technology should they keep an eye on?
That's a good question as well. If for those who just joined this, like who just joined the let's say energy storage research field, I think my advice would be like what kind of project, like sometimes you are not quite flexible to select what kind of project you can work on, but you always want to look into the fundamentals. So this is very similar to all the let's say PhD studies. Let's see, you will be always given a very narrowed project to solve some very particular problems in your area. But that does not necessarily mean that you cannot apply those training process or the knowledge to some other problems once you graduate. So my suggestion would be whatever your topic will be given in, let's say, clean energy technology or energy storage, I always hope you can understand the fundamental behind this technology or behind your project, and then try your best to solve some problem in this narrow and focused area. And by the end of this training process, I would expect you to have a much broader understanding, fundamental understanding about all this field. And by the end of your PhD training, I hope whatever project you were given that's related to energy storage or clean energy technology, you should be able to do a quick literature search and know what's the key challenges here and propose your own ideas on how to solve these challenges. I think this is a key to be successful during your graduate training, no matter what kind of topics you were given.
Thank you so much for your invaluable advice. So is there anyone with any other questions?
I don't really have a question. I would like to thank very much Shuya for taking the time. The talk was very informative and also sharing her experience in the path towards the graduate studies and becoming an assistant professor. And we are lucky to have you here at UNM, and thank you again for accepting the invitation.
Thank you so much, Irene, and it's my pleasure to share my research and my experience to a general audience, especially for women who are working in this engineering field.
Thank you so much. Aisha, the floor is yours.
Oh, thank you so much. If there's no one with any other questions, I think we can say goodnight to everyone by now. It was a very informative talk, and we thank you so much for your time.
Thank you.
And I'm going to share with you definitely the link to the video, just in case you would want to share it with your acquaintances. Thank you so much.
Thank you.
Thank you so much, everyone. Have a very good night.
Have a good